Hi, Moritz.
Hi, Peter. Good to see you.
Yeah, good to see you too. Welcome to the video podcast on everyday metallurgy.
Yeah, thanks. I appreciate the invitation. And happy to have a discussion with you on our today's topic, amorphous metal technology.
Yeah, metallic glasses,
Or
or
metallic
what you
glasses,
call.
yeah.
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 Yeah, Moritz, we have met as a part of our work within the Powder Metallurgy Association in Europe. And you have always been an energizer
Okay,
in the
thanks.
society, a person that I has been attracted to, professionally, of course.
Okay.
But I've always wondered, how do you become an expert in amorphous metals? What led you to that? So, can you give a short introduction to yourself,
Sure.
your name, your educational background, and why or how you got the interest of doing what you do today?
Okay, sure. Yeah. My name is Moritz Stolpe. I'm now working as a freelancing consultant, focusing on metal processing, including additive manufacturing or 3D printing, how it's called sometimes as well. And yeah, my background lies in material science and engineering. I started studying that in Germany, Saarbrücken. This is the let's say city or town that I was born in, and I started studying there in 2003. And then I think the first time I heard about amorphous metals was in 2006 during a lecture that I took. It was amorphous metals, and that was held by Professor Ralph Bush, which came new to the university and brought that topic from abroad. He previously worked at the Oregon State University. So that was something entirely new to me. And I said, okay, I learned a lot about lattice structures and crystalline metals and other crystalline materials. And at the beginning, I was not aware of that there exists the possibility to make metals also or maintain their amorphous structure and get a solid metal with an amorphous structure. So that intrigued me. So I decided, okay, that's new. Let's see what he can tell me about. And I found that topic always, it was always of high interest to me because what you mainly learn is all about the equilibrium states, mainly when you're starting studying, right? So everything is phase equilibria and so on, and thermodynamics and equilibrium. And this was out of equilibrium and was a different, it added more aspects to what I knew at that time. So yeah, I went abroad for 2 years, 1.5 years. I studied in France and then another half a year in Sweden, Luleå. So and at that time, I had to search for where would I write my diploma thesis on. And so when I got back to Germany, I started working in the lab of Professor Ralph Bush and started, I think it was in 2008, and when I started making the first amorphous metal alloys using an arc melter sitting there as a student. And that was the time when I decided to write my diploma thesis at this chair. And that was on mechanical behavior of amorphous metals, in particular size effects, because depending on the size, and this is related to their atomic, let's say, deformation mode, they can either show plasticity or not. And so that was something we wanted to get a better understanding at that time. So yeah, then I wrote my diploma thesis on amorphous metals, and later on even took the decision to write my PhD thesis on it, which was more about the interplay of how multi-component alloys. We did synchrotron diffraction studies to look at the structure, which is a bit more complicated compared to crystalline materials. So we went to these places to do X-ray diffraction studies on it and to gain better understanding on why specific alloys have better glass forming abilities, and in general, let's say, call it structure property relationships with a focus on their rheologic behavior, which means how they change their viscosity with temperature. Because that's basically the key to get one of the keys that how you can make an amorphous metal is having slowing down the dynamics of these melts and avoid crystallization.
Okay. Yeah, I've already learned a lot. And you also gave me an argument now why I never studied thermocalc. The reality is that I never really understood the thermodynamics, but now I can say that when working with amorphous, you cannot use it anyway.
Yeah, I mean, you can use it a little bit, but it's limited because often you have let's say, supersaturated solid solutions, and you have metastable phases that occur like quasi-crystalline phases. And as long as they are not in the database, right, the software cannot tell you what happens exactly. When it comes to amorphous metal formulation or alloy formulations, it's basically a lot of experimental work needed and trial and errors and smart guessing, I would say, having a rough understanding on what makes a good glass former or not. But in the end, you have an idea and you have to show that it works. And I can tell you from my experience, it not always does. So you think, oh, I have a good idea. You try something, you put these alloys together, and in the end, didn't work out. And sometimes surprising things happen, right? So totally unexpected things. So limited use in terms, but for thermocalc. But I don't want to talk it down. So there's certainly some value in using this software.
Okay, thank you. So let's jump into it.
Okay.
Can you describe with words for my kids also to understand what is metallic glass? What is an amorphous metal?
Yes, I will try. So I hope I can.
My kids are 20 plus. So
okay,
it's not for a 6-year-old.
A little bit easier.
Yeah.
Okay. I mean, as you might know, most conventional metals have a crystalline atomic structure. And crystalline means that they have smaller regions in which the atoms are arranged in a very periodic manner. So they are very ordered, right? Every atom has a specific side, and then others fit in these sides, and you have clear distances in between the atoms, and a lot of properties that crystalline materials have, right, are, let's say, determined by their lattice, what you call lattice structure, because it looks like a lattice, a 3D lattice. And in contrast to that, amorphous metals have a disordered atomic structure. So the atoms are basically more or less arranged randomly in space. And so the underlying mechanisms for deformation or corrosion and other properties that these materials have, or that crystalline metals have, conventional crystalline metals have, do no longer apply. And therefore, this disordered structure translates into a very specific spectrum of properties for amorphous metals. And so it's basically the short answer is crystalline metals, conventional metals or alloys have an ordered atomic structure, and amorphous metals have a disordered atomic structure. And disordered, in the terminology of material science, is called amorphous. So, and the fact that they are also called metallic glasses is because the amorphous solid state is called a glassy state. And we all know that from window glasses, oxide glasses, which also have a disordered atomic structure. And that gives them some special properties too. There's also crystalline glasses, but So that's why the material science terminology refers to as a glass, which I think is a little bit more misleading because people think about window glasses and LED glasses and stuff like that. So let's say, the commercial community or industry that is working with these materials usually refers to it as amorphous metals because it's better understandable for others, and it doesn't give the impression that you're talking about oxide classes or that you can use for windows or something like that.
Okay, so you said many properties of a metal is given by the lattice structure, and then when you don't have lattice structures, do these properties difference a lot? Is it physical properties like resistivity, conductivity? Is it changing the density?
Yes, all of that somehow. So,
Yeah.
If you have an amorphous structure compared to a crystalline structure, then this has quite a lot of influence on the deformation mechanism and the fracture mechanism, which in turn means you have different mechanical properties. And so normally in these crystalline materials, you have small defects, which can be, and for plastic deformation, for example, what counts most is dislocations and grain boundaries. So basically defects in the ordered structure. So some areas that are less ordered, and they provide a pathway, an energetic pathway for plastic deformation. So either these different grains slide upon each other over their weaker spots, which is the grain boundary, not always, but often. And then you have dislocations, which are one-dimensional defects in a lattice structure. So additional atom planes that actually shouldn't be there from an energetic point of view, which lower the activation energy for plastic deformation, meaning that atoms can slide upon each other, more or less. And those determine the mechanical response of most crystalline materials. And amorphous metals do not have this lattice structure or these corresponding defects. And as a result, they have a much higher elasticity comparable to amorphous polymers, which can be up to almost 2% of elongation before they start plastically deforming on the atomic scale. And that results in usually a high strength and a high hardness as well. And also a good resilience, that means capacity to store elastic energy. Because if you can strain the material more elastically and it has high strength, then there's more energy you can basically store inside as elastic energy inside the lattice structure or in the material, and that is sometimes used for example, in applications where you want a high elasticity, like springs or so. And that's only one of the things or the properties that amorphous metal have. Another is, for example, their corrosion resistance. And that is also, that is related to the fact that you have basically no different phases. And a phase in material science means an area with a specific concentration of elements and different chemistry. So often normal conventional alloys, multi-component alloys, have these different regions with different chemistry, and they basically
microsegregations.
For example, and they have different electrochemical potential. So then electrons can move, want to move from one element to another, when they have a bridge, so to say, so that they can use, like in a water an aqueous solution or something. And so this in an amorphous metal, the atomic structure is uniform. So all the atoms are distributed randomly, more or less. So there's no phases or grain boundaries or dislocations. All these kind of things are not there. And the grain boundaries for corrosion can act as preferential initiation sites. So the corrosion can attack these parts better because there's a disturbance in the atomic structure. And it's easier to remove atoms or react with the atoms at these specific places. So the more uniform electrochemical potential and the fact that there are no grain boundaries or other or phase boundaries usually leads to a high corrosion resistance.
Yeah. And so that was mechanical properties, chemical properties. So the physical properties, are they also changed, like conductivity?
Yes. So in general, the conductivity, that means the thermal conductivity as well as the electric conductivity, is lower for amorphous metals.
Yeah.
And that is related to the fact that these ordered lattice structure can basically or allow the electrons, right, the charges to move without scattering. And so if you have a disordered structure, a more random structure, then the propagation of electrons, so to say, becomes more complicated. They get scattered more, the waves, and that disturbs their electric conductance or thermal conductance, because thermal conductance always, at least partially, right, is related to the electronic structure. And so that means the materials in general have a lower conductivity or transport properties compared to crystalline metals, but they are at the lower end, so they are still metallic-like. It's not like an insulator or something like that. It's really at the lower end of what a metal can have, but still the electrons can move freely because of the metallic bonding that still exists, and that's still the nature of the bonding. So in that case, I would call them still conductive materials, but with a lower conductivity, generally lower conductivity than crystalline materials. Or not materials, metals.
Yeah. And I remember when I was studying, I heard something about amorphous metals, but we didn't go deeper into it. So is it something entirely new, or has it been there forever? Are there historical data on amorphous metals, or did it come with your time of developing it?
Oh no, I'm not that old, but so I might look that old, but
no.
So they were actually discovered, accidentally discovered in the 1960s, but at the Caltech, California Institute of Technology, at the research group led by Paul Duvet, or Dues, I don't know how to pronounce it exactly, but he was Belgian, so I would assume Duvet, but that might be wrong. Yeah. But they were studying basically solid solutions, supersaturated solid solutions. So basically, where you have two ingredients, and then normally they should decompose into these different phases at some point. But they wanted to understand how much can one species be dissoluted in the other one, without forming these heterogeneous microstructures, without decomposing. And the way you do that is you basically quench the melt or the liquid state. So in that case, the melt, if you're talking about alloys, fast enough to avoid that these atoms can move and segregate into different kind of chemical or in different chemical positions or areas of different chemical position. And so that is also used in classical metallurgy, let's say, even in steel, right? To make supersaturated solid solutions like martensite, for example, where you have basically you have too many carbon atoms, and as a consequence, you get a new atomic structure when you quench them rapidly enough, right? And that's what they did. They quenched these alloys in splat quenching. They took small droplets and then squeezed them into two, I think it was silver plates. And the idea was to study, okay, how much can be dissolved, silicon can be dissolved in that gold until and in the end, when they did X-ray diffraction, so that is something you do in order to understand what structure has formed. They figured out that the signature that you normally get, so Bragg peaks, right, were no longer there, and it showed the typical, let's say, response in that let's say characterization technology for an amorphous material, which was pretty new and unexpected, because I think up to that point people did not believe that it's possible to make amorphous metals or maintain the amorphous structure that is inherent to the liquid and bringing it into the solid state by fast enough quenching. So that's how it started, so in the 60s. And then this was, as I said, primarily on a gold silicon eutectic. Later on, people then started, and that was mainly in the 80s, 90s, started to working on improving the class forming ability, right? And in order to understand it, I think it's helpful to look at a so-called time temperature transformation diagram. And I have prepared one, so I can show you.
Yeah, so, please share.
So I that should hopefully help here. And let me. So now you should be able to see how glasses are formed. So what is shown here is the typical time temperature transformation diagram, which is here just schematic. So, and these time temperature transformation diagrams basically tell you what is the stable structure or what is the stable state at a given temperature and time. So here you can see the liquidus, which is basically the melt temperature. Above the liquidus, the material is a liquid, right? It's stable in its liquid state. So you apply heat, and at some point the metal melts. So, and that occurs at a more or less defined range. In that case, it's a little bit simplified by a line, but in most cases, it's rather a range. And above that liquidus temperature, the material is stable in its liquid phase. So that's the most energetically most or thermodynamically most stable phase here. What happens if you cool it down? Then normally, under moderate cooling conditions, and this is shown here by the red line, you are crossing what is called the nose of crystallization, because it has this T shape here, looks like a nose. And once you cross that, atoms will rearrange from their amorphous structure, which is shown here on the lower picture, and will arrange into a highly ordered structure, which is a crystalline structure. So that happens under moderate or slow cooling. And these amorphous structure that is inherent to the liquid state, so in the equilibrium liquid, you can maintain if you cool fast enough. So, and that is shown here by the green line. And if you if you achieve to circumvent these crystallization nodes, to cool it quicker than and bypassing this nose, then the material becomes denser and denser and denser. Atoms becoming closer together and together because the volume shrinks during that. And the closer they get, the more difficult it becomes to them also to move. And also you're removing heat out of the system, and heat means kinetic energy, and kinetic energy means atoms can move easily. So, and at a certain point here, at a certain temperature, which is even time dependent or dependent on the cooling rate, the viscosity of that liquid becomes so high that the atoms basically freeze in at their positions. So that is the point where you can maintain the amorphous structure that is inherent to the liquid and bring it into a solid state, because then you no longer have a liquid, but you have a frozen in liquid, and the frozen in liquid is considered or is called a glass in the scientific community. So you end up with an amorphous solid that is made from a metal, and that was something new. So that's how it works in general to make these glasses from a theoretical point of view, right?
Yeah.
The difficulty is to find the alloys that can do that.
Yes, and that was exactly the question I was looking for, because how do you find alloys that are that has a what you call a short nose or a long time for undercooling the liquid? I know for heat treatment of steel, if you want to avoid the formation of ferrite and bainite and so on, if you add just a little molybdenum, then your nose will just grow dramatically.
And that is exactly how you do that. So you're trying to shift the nose to the right?
Yes. Yeah.
Because you're limited by the cooling rate that you can achieve, or given on the technique that you're using, the cooling rate is more or less something that is, rather from a processing point of view. So you can change the technology and improve it, but there's a certain limitation to that. On the other hand, you can also work on the material itself, on the alloy, and try to shift that nose towards the right, which actually means that if I would move that nose even more to the right, that even the red slow cooling rate could bypass it. And in that case, I would have also an amorphous alloy. And that basically can be done by making the crystallization more complex. And as I said in the beginning, so they were discovered in the 1960s based on a gold silicon eutectic. And a eutectic is an alloy composition in the phase diagram that has the lowest melting point. And the lowest melting point automatically means that compared to the competing crystalline phases at lower temperature, the liquid with its disordered structure is energetically more stable. So because the lower is the melting point in your compositional space, then the lower you can go in temperature without crystallizing the material. And then it's easier for an alloy to be brought into the amorphous state, because basically the liquidus is lowered here, this horizontal line. So and the temperature difference that you have to basically overcome, and getting it from that liquid state to the glass becomes smaller, and so that is easier to achieve by different, let's say, processing technologies. Or you can then even go from one technology to another, which I will explain in a couple minutes. But I would just add a few sentences on how to get to better glass formers. And if you look here on the picture or figure on the right, then you show what is called the critical casting thickness in centimeters versus the year of discovery. And the critical casting thickness, that is a material property that is used to classify amorphous metals in terms of their ability to become amorphous at a given. So that means that is the maximum thickness or wall thickness that you can produce for a specific alloy, where it would still be amorphous, and beyond, if you would like to, if you would cast something thicker than this, it would crystallize already, and below it would not crystallize. So that's basically the boundary of telling you that's the maximum size of my castable product or cast product that I could get from these alloys. And as you can see from that chart already, one of the idea was, and also how they achieved it, was to develop more complex alloys, going from binary, very simple systems consisting of 2 elements or 3, into more complex alloys, having, for example, 5 or 6 ingredients or elements, so to say. And when you do that, you have to consider a couple aspects. One that I talked about is the enetic stabilization of the liquid phase, which means you are searching for near eutectic alloys. So in all the compositional space, you're you're usually trying to go something that has already a low melting point for the reasons I mentioned before.
Yeah.
And another one is that if you do that in a multi-component space, then normally the global minimum in that space for the melting temperature can be lowered, right? So that is one aspect. So near eutectic means thermodynamically stabilize the liquid against crystallization. Then if you have multi-component alloys in which the size with atoms of different sizes, even in the disordered state, you can fill space more efficiently. That means you get a denser liquid structure. And the denser is the liquid structure, the more difficult it is for the atoms to move. So diffusion becomes lower, or atomic mobility becomes lower. And then you have a kinetic stabilization of your liquid or amorphous structure. And if then you have multi-component alloys that would crystallize into different phases, so different region with different chemistry on an atomic level, then these different elements need to separate and redistribute, and that requires atomic motion. So the more complex you make crystallization and the more sluggish you make it, right, the more your crystallization nose will be shifted to the right, and so the less or the lower cooling rates are required to get something into an amorphous state. And there's also an empirical formula that is shown here that basically shows the relationship in between what is called the critical cooling rate, so the minimum rate that you need to apply to circumvent this nose of crystallization, and the maximum wall thickness you can cast for a specific alloy.
Yeah. So just to sum up, so if you have a mix of large atoms with smaller atoms, then you can place the smaller atoms into the structures, making it more dense. So like if you have spheres, you can put small particles in between the big ones. Then it's more difficult to move them. Is that right?
Yes, that's correct. Yeah. So you basically form elements, or you densify the overall structure by allowing smaller species to fill space and the overall alloy to fill space more efficiently, and that leads to kind of a densification. And a denser liquid means it has a higher viscosity. So normally a metal at around its melting point behaves like water.
Yeah.
These amorphous metals rather behave like oil.
Okay.
Because even if they are stable at that point, their packing density is so high that the atomic mobility is lower, and at lower atomic mobility means higher viscosity.
Yeah.
And so, you can basically picture that similar to the difference in between oil and water.
Yeah. Okay. So when you're looking at your list, I recognize alloying elements like phosphorus to be in metal powder industry. We call that a liquefier. So if you want to make a liquid phase sintering, you can add phosphorus and lower the solidus temperature.
Yes.
You can also use boron. So is that also used as a glass formation element?
It is, especially for the iron-based materials and nickel-based materials. So because there's a good, let's say, size mismatch in between them.
Exactly.
And also from a thermodynamic point of view, you often find eutectics, so compositions that have low melting points. And it turns out that iron phosphorus and iron boron are actually, even as binary alloys, can be brought into the amorphous state by still relatively high cooling rates. So using a technology that is called melt spinning, which was also I think the first commercial or industrial way of producing amorphous metals at all.
Mm-hmm.
So,
yeah.
And this is something that you see here, and it also visualizes the interplay in between the alloy properties and the critical cooling rates that were put on the previous slide, and the resulting, let's say, dimensions of your product. Because if these very early binary alloys like iron, phosphorus, and so on, and like the gold silicon, this was even worse, they required cooling rates in order to maintain their amorphous structure or to become an amorphous metal or a metallic class of about 1 million Kelvin per second, which is quite a lot.
It's been fast.
Yeah. So you cannot just throw them into water like in steel. And so the way to produce then amorphous metals was more or less limited to, or the products you could make were limited to thin products like foils and ribbons. And they were created by the so-called melt spinning technology. And they are still produced in that way, where you basically pour the melt onto a rotating wheel.
Yeah.
And so
like neodymium iron boron magnets are produced with this technology.
Also, aluminum silicon alloys, right, are often produced in that way for space industry, for mirrors or something. Afterwards, you create something like a flaky powder, and then you hip it into something into a different shape. And so, melt spinning is not only used for amorphous metals, for sure, but it has been, I think, the first way of producing amorphous metals in an industrial environment, because the technology was there, and it provided high enough cooling rates to make these, let's say, marginal class formers to still make them amorphous, even though their class forming ability was relatively low, or the overall critical casting size. But with the development of new alloy systems like here, like the zirconium-based ones and so on that are here shown here around in the 90s, since these alloys only require cooling rates of about 1,000 Kelvin per second or even less, you could change that and also use die casting or injection molding by directly pushing the molten material into permanent molds or tools, and where they would solidify fast enough to avoid crystallization. So that is a good example of how material science and further alloy development really made a difference in terms of the products you could produce, because only by developing these improved glass formants, new processing technologies and opportunities became available.
But the first method, you could say, the melt spinning, that's a powder metal process. And you have been working a lot with powder metals and 3D printing of this as well.
Yes.
So is it material that are melt spun that you use for 3D printing, or is it gas atomized, or well, how do you do that?
So you could do it. There are attempts to use foils to 3D print BMGs, so adding foils on top of each other. But what I have been doing, we have started from powders. And let me see, I have another slide that I can show. Meanwhile, I'm going to talk a little bit more. So I would say the industrially most mature technology to produce these materials is actually based on powders, not so much the here. Let me. I'm not sharing anymore. Sorry. So so there are different ways of how you can additively manufacture amorphous metals, and the overall idea is to decompose class formation, so the step of making it amorphous, from the overall shaping process. because as you can imagine, if you pour something into a mold, right, and it has a critical casting thickness of 3 millimeters, your wall thickness can never be more than 3 millimeters. Otherwise, the material crystallizes because the cooling rate is just not high enough. The heat is not extracted fast enough outside of your melt to avoid crystallization. So, but with additive technologies, due to the layer-wise formation, you can decouple that, let's call it glass formation, from the shaping process. And either you can use powders, and I think the most commonly explored technology is laser powder bed fusion, which is also the most mature from a commercial point of view, an industrial point of view. But it has also been shown, at least in research, that laser foil printing works. So you add one amorphous foil that is produced by melt spinning, exactly as you said, onto another, and then you weld it to that using, for example, a laser. So that is something you can do. And also similar to that is ultrasonic additive manufacturing. So you're starting from sheets and you apply a high frequency motion. And so basically you're welding the individual slides together using vibration. And that works. You're basically destroying the oxide layer and then pushing the material together and enabling the metallic elements or atoms to feel each other so that they can create a bond in between. So the key here is to break the oxide layer that exists, the native oxide layer, and then to kind of cold weld the material together. There's also other attempts using laser direct energy deposition. In that case, you're using a laser and you're with a nozzle, and the nozzle you're shooting powders onto a target, and the laser melts the particles and creates a melt pool, and you basically throw in your material into that melt pool, or you melt it even while they are flying through the laser light. So that is another technology. And there was also Desktop Metal trying to use amorphous metals for fused filament fabrication, like thermoplastic polymers. That's possible because as thermoplastics, you are in an amorphous state, and heating up the material will give the atoms, will allow the atoms to gain back more mobility. So above the glass transition temperature, similar to polymers, the material acts like a highly viscous liquid. And that allows you to use that process. But it has a lot of disadvantages, and it's much more difficult compared to polymer. So I'm not convinced about that approach, to be honest. So
what temperature are we typically at there?
Depends on the system, but let's say for most commercially used amorphous metal alloys, the glass transition temperature lies somewhere in between 300 to 500 degrees Celsius.
So you also put some pressure on the equipment.
Yes, that is true. And you, since you are working at elevated temperatures, oxidation and all that comes into play. And so I would say the fused filament fabrication of amorphous metals might not be the best approach among those. I think the most promising so far, and I'm not saying the most promising is maybe the wrong wording, but the most mature technology is laser powder bed fusion of amorphous metal powders.
So now the big question of today, Moritz.
Yes.
What can we use this for? What are the applications? How do you make your salary?
Well, I'm not only working on amorphous metals, but to a large degree, I do, admittedly. So, these there's different answers to that. So depending on what we are talking about, I think still the largest impact or commercial impact of amorphous metals is melt spun foils that are used due to their soft magnetic properties, which we haven't talked about yet, but they are very soft magnetic. And so they are used, for example, they are like electrical steel, They are stacked together, the melt spun foils, and then used, for example, as transformer cores or for electronic article surveillance. And there are other, let's say, applications where they are highly soft magnetic behavior.
Yeah. Which alloys? Is it iron-based?
It's iron-based or cobalt-based alloys, or iron cobalt and iron nickel. So there's a variety of different alloys that can be used. I mean, I can show a slide here. I don't want to do marketing, but at some point you have to show, right?
Yeah.
I can tell I'm not paid, right?
Okay.
So it's just a slide I had. So here you see the so-called MET class foils produced by Proterior, which was formerly Hitachi Metals. And it also shows some of the applications and also provides a figure how it's produced, right? This melt spinning process, here they also have it automated. So with a hot rolling process and a strip winding, what they call it. And so, but those are typical examples of the products you would get from these foils that are used for soft magnetic applications. And another company active here is the vacuum smelter, which and what they sell this under Vitrovac. And as you can see, the benefits, they say highest permeability, high remanence, and low losses. And it's usually the low hysteresis losses in combination with the low eddy current losses that are of interest because of the stacking. So that is why they produce these foils and ribbons. And you can see here that they offer cobalt-based, iron-based, and that's basically the main two groups. And they often include also nickel. There's also nickel-based, but they are not that well suited for the soft magnetic due to the nickel. It's worse than the cobalt and the iron, but they consist of nickel too in most cases.
Okay.
Or in some cases.
Yeah. So you can go to higher frequencies in applications without having higher losses. But due to the high saturation level, you can keep your components small. That's the advantage as I see it.
Yes, and let me show this. So the claim they make, and I have to say I never tested that myself. But for example, Metglass claims, right, or the Office of Energy Efficiency in Canada said that these amorphous core transformers offer up to 70% lower core losses than conventional transformers, which is which is a result of their amorphous structure, right? Not having the different grain boundaries and that block the domain motion. And so they can easily magnetize, demagnetize with low losses. That, as you already said, is very promising or of interest, of high interest for any applications that requires changing the magnetic direction back and forth at high frequencies.
Yeah.
Or even lower frequencies, like in this transformer course.
Yeah.
So that is one of the examples where they are used. Yeah. But there's more to it, because this is only for the foil and ribbon-based materials, and others are. And I'm just throwing that on again. I don't want to make marketing for the companies, but you have to. I want to give them the credits, right?
Yeah,
because
that's
it's not
perfect.
my pictures. So, for example, one of the oldest companies working in this what is called bulk metallic class business or industry, and bulk means alloys that can be cast with a thickness of at least 1 millimeter thickness to discriminate them from the foils industry, though they are called bulk metallic classes.
Yeah.
And you
so
can see a couple
for injection molding.
Yeah, for example, die casting or injection molding. And here you can see a couple of applications, right? So it's usually thin-walled parts that are complex to manufacture and require higher strengths compared to polymers, for example, require a high surface finish, because the fact that these materials are so dense in their liquid also means they have low solidification shrinkage. And that means when you cast them, you can get a much higher precision compared to MIM, which has to go through sintering and so on, right?
Yes.
You can achieve single-digit micron tolerance levels by just from by using, let's say, of course, you need the mold to be highly precise then, but the material.
But its dimensions out of tool.
Yeah, it's out of tool, and it has a very good repeatability. So it's very highly reproducible. And yeah, you can see some applications, for example, in housings, electronic brackets, or medical devices, instrumentation, for example, here. You see, there's more to it. You can use them as spring materials due to their high elasticity. The same applies for sensors because you can strain them much more compared to crystalline materials. Let's say even spring steel, you can basically use 0.5, 0.6% elongation until it deforms or breaks. In this case, it's up to 2%. So there's more strain available, so to say, more elastic deformation available. There were golf clubs. I don't play golf, so I don't know how they perform, but that was something that is quite popular.
Yeah.
Then, due to their elasticity, they also have specific acoustic properties, and there's much more. Maybe something that has been explored recently, and the company active here is Amorphology. They are making gears out of these materials. And that stems from initial research or previous research at NASA, where they have demonstrated that for space applications where lubrication is difficult, right, because of the low temperatures and
vacuum.
Exactly, vacuum, that these BMGs, so specific BMG alloys, perform very well, much better than steel in unlubricated conditions, with a more than an order of magnitude longer lifetime, which for space applications often is enough. And then, because they are not necessarily need 10 million cycles or something like that, right? When they do that, but it's not, the lifetime is still lower than lubricated steel gearbox, but the unlubricated, but in unlubricated conditions, it performs much better, and that's also very promising. And that, I think, is the natural next steps, is to explore. Does that also translate into more industrial conditions, relevant conditions, right? Under lubricated conditions. So far, I think what has been demonstrated is that they provide superior performance in unlubricated conditions, space-relevant conditions, and the next natural step is to explore also other markets and applications where they might be lubricated and still have a lifetime increase of a couple X compared to that, because that would make them interesting as well. And those are just a few applications. I think personally, medical requires qualification and so on, is something that is highly explored. Watchmaking industry is using these materials. Gear industry, robotics industry is looking at it. There's more. There's electronic connectors you could do. There's sensor technology, as I said. Sometimes you can use these foils for brazing. You can come up with flexible bearings or compliant mechanisms that take advantage of the high elasticity. So I would say applications. What is a good application for BMG? For if it's not about the soft magnetic properties, if it's about the structural properties, then I would say something that requires a high elasticity and a high strength in combination with the manufacturability via die casting or injection molding, where you can create complex shape components with a very good surface finish in much less manufacturing steps compared to other technologies. So that is where I see the main application also in future.
Which alloys did you just present here? The soft magnet was iron, cobalt, nickel based, but
yes.
What are the gears made in?
The gears are often, so I would say the most explored and most widely used materials for commercial aspects for this BMG business, right? Bulk metallic glasses are zirconium-based alloys, which often, based on a zirconium, copper, aluminum base eutectic formulation, and then modify it to with other elements to improve glass forming ability or improve specific aspects or properties. Then also nickel-based, niobium-based have become now something that a couple companies are looking into also for medical applications. Then magnesium-based is something, and calcium-based, something that medical industry is interested in, does R&D, because they dissolve in the body. And due to the higher corrosion resistance, the formation of gases occurs slower, which is actually beneficial for the patient. So, so that is, I'm not aware that this is solved already, but there's promising R&D work, and ETH Zurich, for example, is doing a lot here, among others. And so that is also something, maybe a future application. But so far, getting back to your question, it's mainly zirconium-based. There are nickel-based alloys, and there's niobium-based alloys that are used. Sometimes it's copper zirconium-based alloys that are also used for gears and so on.
Yeah. So still in the group of what we call exotic materials.
Yeah, I mean, it's still a quite exotic material. It's still a material that finds application in niches. Yeah. And one of the reasons is its costs, right? And I would say, so the manufacturing or the manufacturing aspects, right, that do not necessarily make that expensive, but it's the alloy formulations. And especially the alloy raw materials, or the raw materials used to make these alloys, need to have a high purity, because let's say impurities will lead to the formation of smaller nucleation sites, and then it's more difficult to get them into the amorphous state. So that is why high purity metals are normally used or required to get the best out in terms of glass forming ability and avoid crystallization. And that, on the other hand, is needed to give them their specific properties. Because if the material crystallizes, then often you lose all the interesting properties. And so, that is something that the industry, I would say, is still struggling. Might be too hard, but it's still a challenge to find cheaper alloys, or maybe even to scale up, right? It's a little bit this chicken and the egg problem as well. So unless you have found many applications and build up a huge industry, like in steel, which has grown over quite some time, right? Then it's still exotic. The volume production volumes are low, which makes it more expensive. And then on the other hand, in combination with the relatively expensive raw materials, then the alloy costs are relatively high. Yeah. But from a manufacturing point of view, the fact that you can it's fully automatable, right? All these injection molding, die casting processes. Yeah. And you save some energy by not having the need to do a lot of post-processing due to the good surface finish and also the near net shaping formability.
Yeah. Then the low temperature is also beneficial in your energy consumption. But the low temperature might also be an issue in what temperature you can use the product at. So because typically when you heat treat, if you go down into your stable zone, it stays stable. But then what happens if you heat treat such a gear at 300 degrees? Does it recrystallize or is that
there's definitely something. The crystallization is something to consider, And I'm just putting on this slide again where it shows you the time temperature transformation diagram. So once you have achieved the fast cooling and you're in the glassy state and you heat it up to a temperature above the glass transition temperature, which would be above that darker gray area here. Show if I can get this pointer here. So beyond that line here, then you have only a limited amount of time until the atoms will find their way into the equilibrium structure, which is the crystalline structure. And depending on where you heat it up and hold the material, this can be from infinity to only a couple seconds, right? Because this is on a logarithmic time scale. So if you are close to the nose, it's probably not even a few seconds or even less, even for good glass formers. But if you are operating here, it can be a couple minutes. But even some hours when it comes to just storing them. In general, you say that you should stay below the glass transition temperature. And the glass transition temperature for the zirconium-based alloys is normally in between 350 to 400 degrees Celsius. So you should definitely, to be safe, stay below, let's say, I would not recommend using it over 250 C or something, an alloy like that. So at least 50 to 100 Kelvin or degrees Celsius below the glass transition temperature, then the material is still or the atomic mobility is so low that basically nothing happens, right? At least on the time scale of a human life being. So because it's just frozen in liquid, it's not, so there is something going on, but even in solids, right, you have solid state diffusion. So it's hard to prevent any atom to move somehow, even at low temperature in the solid state.
But it was better than I thought, because I was thinking if you put a gear like that into space and the sun is shining, it could be 50 degrees on the sunny side. Will it destroy itself by that? But it sounds more robust than I thought it was.
Okay, I'm happy. So they are not that unstable, but once you are getting close to the glass transition temperature, then it's becoming more complicated, and you have very limited time. So you have to be sure that your time or temperature time window during processing or during the application will not lead to a degradation of the material, and degradation here means crystallization, or as a result of crystallization, degrade in terms of its properties. So but one thing is for sure, you cannot use them for high temperature applications. So it's not a nickel-based super alloy or something like that.
No. Moritz, I have a last question.
Sure.
I would like to put on the podcast today. It's a question to looking ahead into the future. How do you see these alloys become a part of the future? Looking at the possibilities with AI, can AI help find new alloys that has a wow, why didn't we see that before effect? They talk a lot about making these high entropy alloys using AI, because then you can mix and you can just make 1 million of artificial tests in AI world and then find the alloy that you're looking for. But does it have any help here?
Yeah, it would definitely have an help, as it would have for finding improved crystalline materials. So I think in general, material science will definitely profit from all that technological advancement in the field of AI, and also computational, so molecular dynamics computations, right? Even more basic fundamental calculations. Density functional theory, unit cell, that they can simulate and screen much quicker now. The processing capabilities are getting better and better. So there's definitely something that will help for exploring which help to advance material science and also metallurgy. I'm sure about that. I think the key would be to find alloy systems that have similar class forming ability that, let's say, currently used alloys have, but that could be produced from lower grade materials. For example, because, as I said, one of the big things is the material costs. If you go to very small parts, it does not really matter, right? And also what I think will help will be 3D printing, because that will definitely enable to overcome, and it has been demonstrated already, that you can overcome the given size limitations for amorphous metals and create larger parts. And what is also still a topic, an R&D or innovation topic rather than a commercial of exploited topic, is amorphous metal composites. Because amorphous metals have a high strength, but they have a downside that comes with it, and with their disordered atomic structure, and that's the shear softening, similar to adiabatic shear bending. So under purely tensile straining conditions, they deform and fail in an apparent brittle manner. So there's no ductility, there's no tensile ductility for amorphous metals. And that is something that from, let's say, industrial point of view is also quite limiting, because a lot of engineers look for these properties, and let's say a certain amount of tensile ductility is kind of needed for them. And this monolithic metallic glass that means a purely amorphous structure of a glass, not a composite, has no tensile ductility. So it would always fail immediately before starting to deform plastically due to the strain softening that happens. But if you manage to incorporate something like a soft crystalline phase, that can block the formation and propagation of shear bands, and that is where they slip along and rupture apart. So it blocks the formation, and so a new shear band needs to form. So basically you can delocalize the formation by stopping the propagation of shear band through the entire material. So bifurcating, so to say, the shear bands and multiplying the shear bands, and that gives you also tensile ductility, and that has been shown. And I think that is also something that might be used in future to overcome at least that disadvantage that current monolithic metallic glass formers have.
Yeah. Wow. Sounds like if you have still a few years of work to do.
That's true.
And also a lot more, because one of my reasons for making this podcast series is that I want to show the young generation that material science is not for the old gray men. It's really needed to bring us into the future.
That is true. And I mean, there's much more. Today I talked only about metallurgy, right? But there's so much more in material science in general, right? This is, let's say, a very exotic part of metallurgy. And metallurgy is probably where you picture the old man sitting, right, pouring alloys from one container into another. And in the end, everything is steel and titanium and aluminum and so on, right? It sounds so boring. But it's not at all, right? Even metallurgy, all these new alloys, these super alloys that have been developed, right? These new types of steels, all that, right? The new processing technology, and I know you are also working on that, right? You with your company, new types that are very interesting and allow to produce things that formerly could not be produced by conventional technologies. That are more cost efficient and bring an advantage to the end user, right? In automotive, like security or something like that. So that is also very, very, I would say, very interesting. And what I like the most about material science is it basically includes all the natural science, right? So not so much biology. Sometimes if you go into medical, then it's
Yeah,
true.
yeah.
But let's say at least physics, it's a very good interdisciplinary field of engineering and physics and chemistry, right?
Yes.
And polymers is probably more on the chemistry side. Physics is more on the metal side. But in the end, you need to understand all of that, including processing, right? Technologies. And that is what I like the most, right? It's not so narrow and narrowly confined to something. It's bridging all the different parts of chemistry, physics, and also engineering.
Exactly. Thank you, Moritz. I think we will end here on a high note.
Okay. I could talk for hours longer with you, but
yeah, I know. But I would like to thank you very much for participating and
thanks for the invitation. I really appreciate
giving away your knowledge. I have learned a lot today. So thank you very much.
Yeah, thank you too, Peter. And maybe we can in future have another conversation, so deeper dive or whatever. So,
yeah, it could be. I'll be back with that.
Okay, Peter.
Thank you.
Take care. Bye.
Bye.